Go. I'm ready when you are. Got to get my microscope in, but we can get started until then. Oh, we're live. We're live. Hello, everyone. Hello. Hang on a second. Welcome. Morning, all. If it's morning, your time of the day, of course. Yeah, thanks for joining us on another Teardown Tuesday. A bit of a rushed one today. I'm just getting my microscope feed there. What I might do is bring my webcam. Oh, am I frozen? Why am I frozen? That's not ideal. Sorry, folks. Hey, OBS, do you want to let me be unfrozen, please? It'd be really great if you could let me be unfrozen, OBS. Are you gonna do that, OBS? No, you're not, are you? Because you have been playing up for me lately. Sorry, folks. We will might just get started on taking a look at this here. So, it'd be really nice if I could get that front camera working. I'm really bummed that it's not. That's so frustrating. Let me just try one last thing. We're reasonably on time. Hey, Alec. How you doing, bud? So good to see you. What time is it for you over there, Alec? Okay, well, that's just not playing ball. We'll try just removing it, and OBS does this from time to time, and it's really quite frustrating. There we go. And it sorted itself out. It just needed you to remove all the video sources, reapply them. And then here we are. Thanks, OBS. You're the best. And we can have that under there. This is just my microscope feed. So we'll kind of just put something under there so it doesn't look quite so frozen. Cool. 11 p.m. You're amazing. You're amazing. So welcome to our second Teardown Tuesday. It's 7:04 here for us Australians. And today we are taking a look at the Morningstar Relay Omniport Relay Switching Interface. Make sure you can see that, have the light. So we picked this up for a couple of reasons. We actually had a customer reach out and ask if it was able to be used with our FlexiPorts, and the honest answer was we weren't sure. We weren't entirely sure there. So I'll switch that microscope off while I'm not having any on. Maybe I'll just make me a bit bigger there for a sec. We weren't sure because when you're dealing with devices that use relay switching, the relays are there to provide an interface from a low voltage to a higher voltage. Typically it might just be switching 9 volts or 12 volts or 18 volts, but sometimes it might be 40 or 50 volts, especially if you're switching, say, channels on a tube amp. You want to be careful and make sure you really know what you're plugging into before you just sort of go willy-nilly. And then controlling them is also another thing. I had my doubts because this is it's designed to be powered from 9 volts. Who knows what kind of voltages the relays are expected to be driven with? It won't be more than 9 volts, but is it 9 volts, 5 volts, 3.3 volts, whatever? We're just not sure. So we picked one up, and it's a really, really nice little box. I especially love the assembly and the design of it. So we, of course, are going to take it apart and have a look, and we're going to see how it works, see what's inside, so we can get a better understanding of some of the, in particular, the digital electronics that are at play there. I'm going to get my keyboard out of the way. Bring this down here for you guys all to see. Trying to stay in the light illuminated patch. Sorry if it's a bit glary. The humidity is really starting to drop here as we're getting into winter. So got an anti-static mat just to try and help with that. Actually, what I might do is do that, and then there shouldn't be as much shadowing. Cool. Hopefully you guys can see that okay. Does that look all right to you, Simon/Stream? Hey, everyone. Thank you for joining. Welcome, welcome. So, yeah, we've got these two jacks. We've got an Omni port in, so this will be your control input. Then we've got the relay output. So you've got independent tip and ring switching, then power. That's it. Beautiful blue anodized finish, actually. I'll see if I can pick that up without kind of just getting it in shadow. I really like that. Yeah, that's nice. Really nice shimmer. Those LEDs are tiny, though. Teeny tiny. So let's take it apart. We've got 4 Phillips head screws here. Now, I would assume, like, there are other things, that this will be some... I don't even know the correct name for them. They're not like captive inserts. They're welded standoffs. I guess threaded inserts that have been welded to the enclosure. So, yeah, those things there, they're sort of pressed in. Can you tell I'm not a mechanical engineer? Dropping stuff everywhere. Sorry for the noise. Let's take these off. So not that much going on in here. Small enclosure, so it's not as if you've got the luxury of space anyway. But this looks really cool. Beautiful. So that's held in place there. We've got 1 standoff, 2, 3 standoffs. Ooh, I like that. So you can't even tell on the surface there that there's a standoff. You can't see anything. Let's check that. That's that's super smooth. It obviously hasn't punched through this top surface. That's nice manufacturing. I really like that. So let's take these, loosen these screws. Okay. So they've got rather than holes, they're using plated slots to fasten the standoff here. And I'll show you what I mean in a second. That's interesting. So you can see how I'm able to move it back and forwards. And that's because these screws aren't going into a hole. They're going into these. You should be able to slide this out. They're going into these plated slots, right? And so what that means you can do is you can align it there, get your kind of jacks aligned with the holes, and you'll put your screws in. And it more or less just allows you to control the, that axis of movement to make sure everything's perfectly aligned. And I would assume is there to just account for machining tolerances and manufacturing tolerances. Obviously, just how aligned everything is in that axis is a little variable. So very nice, I have to say. Just make sure I don't lose anything, because there's those. Oh, sorry about that. There's those washers there which will help space the jacks to the enclosure. So straight away, there are our 2 relays. Now they'll just be like single pole switching relays, are they? Oh no, so there'll be a control there, and then you've got switching between 2 contacts. I mean, it's not too important. You're just, you're switching the tip and the ring closed and open, essentially. What type of relay that it is isn't too important. We've got some voltage regulation, some protection diodes there, 1 IC, a couple of what look like transistors, some resistors, and interesting that they've gone a double-sided approach here. I mentioned this in the Strymon Conduit Teardown, where if you're not aware, when you have components on both sides of the board like this, it's called a double-sided assembly. And it can greatly increase your manufacturing costs compared to a single-sided board, but like it all depends. You might be set up to do double-sided manufacturing anyway, so it's not a big deal. Is my face getting blown out in the light a little there, or it's okay? All right. Simon says it's okay, so Simon says. And so, yeah, I mean, my guess would be it's pretty much to do with where those LEDs are. And, if you want those LEDs to be on that part of the enclosure, it's hidden by this jack here. So you have to put them on that side, right? And then if you're putting something on that side, then you might as well put some other stuff on that side. Because the way that process works is you apply your solder paste to the board, then your pick and place loads up with components, and it runs through the machine, goes through the reflow process to solder those components. Then you actually have to turn it back over, apply the solder paste to the other side, put the components on it, feed it back through. So it's extra operations. The EEV block, Dave Jones has some really good videos on sort of, designing for manufacture and some of those different things. But, it was really nice. I would just imagine a 4-layer board. There's a ground plane there. I mean, or maybe not. Maybe it's very simple. It might just be a 2-layer board. In fact, probably looks like you've got all your signal traces here, and then you've got a nice low impedance ground plane. I'm just assuming it's a ground plane there. Yeah, the sleeve of that jack's connected there, so that's gonna be a ground plane. So very cool. Let's power it up and I'll look at the operation. So we've got power. Power LED is lit up. So what we might do is take a look at some of the chips on board and see what's happening. So let me grab a multimeter. All righty there. And microscope. Let's move those screws out of the way, making sure we don't lose them. Morning, everyone. Well, thank you for tuning in. Welcome to our second Teardown Tuesday. What is this? So this is the Morningstar Omniport Relay Switching Interface. This is the enclosure, but really, really nice option if you need to control relay devices from, a MIDI controller. So the question that we had is, it only makes mention of being able to be controlled via an Omniport, and we were interested to see what control options you had available. So we need to see how it works. So just firing up my microscope here. Let's get it in focus. There we go. So we have power on. You can see the LEDs lit up there, even though that's out of focus. I'm going to take these washers off. They're kind of annoying. And I might move my top-down camera to somewhere where you can maybe better see what's going on. I don't know if that helps, folks. Let me know if that kind of an angle is better. I mean, you kind of get my hand in there a little bit. Maybe something like that. See what I'm doing, perhaps? Anyway, we'll see. All right, so power. Now, you can see that we've got power going through to this diode here. So that's a B340 AE. The markings on there are 138. Anyway, that's just going to be like a reverse polarity protection diode, I would imagine. Possibly dropping the voltage as well. Anyway. Now that will be a voltage regulator. So what's that? That's an LD50. On my keyboard, we'll see what. I mean, I can sort of see from the traces what's going on, but we might, just for safety's sake, take a look. Safety to the device, not me. This is a very low power device. LD50 linear regulator. What have we got? I need to make sure for next time I'm screen sharing so you can see the data sheets I'm pulling up. But what I see on the PCB. Hey, Merrick, we'll take a look at that. My guess would be it's some sort of analog buffer or, switching inverter. All right, so do they have this part in the package that I'm seeing? Let's take a look. Or are you referring to this? I see. This will be a voltage regulator. So it's marked. It's an ST part. I can see there the ST logo. Anyway, that will be. It's been a little elusive to find, but that will be some sort of. I would assume low dropout linear voltage regulator. So I need a little keyboard tray, but let's bring up our multimeter and we can safely do some probing. So I know that that's going to be ground. Let me show you there. At that point, I just want to make sure, try and get my fingers out of the shot there. It's not really any better, is it? I'll try for something like that, maybe. That might be a bit better. Oh, but now I can't get my hand in there. Sorry, folks. I'm just trying to make sure you can kind of see what I'm doing rather than it just being my hand the whole time. You know, that might have to do. Sorry. All right. Anyway, we're on the microscope here. So I'm going to switch to a continuity test. So you should hear it beep when there's continuity. I'm just going to double check which of these pins is ground. Are we on continuity? Fun fact, folks, before you check continuity, make sure your probes are on the voltage or continuity sockets, not current. All right. There we go. What is that measuring for all of them? There we go. Okay. So you're telling me they're all ground? Forgot to remove power. Always remove power when you're checking for ground continuity and things like that. Okay, so that pin's going to be our reference pin there. So now let's measure some voltages on this regulator. Got something underneath there. Yeah, sitting on a screw. Got him. Okay, so actually I might bring this around the other side here so I can more easily probe around. He's got like some blue tack or something to hold this down. That sounds anti-staticky. Voltages. What are we measuring here? I know my input's going to be 9 volts. And that's 4.99. So that's likely our output. And that should be our input voltage there. Yep, 9 volts. And 4.99. So the configuration here is that pin there is ground. Let me find the... Yeah, so this pin here is ground. That pin's our output voltage along with the tab, and that's our input voltage. So we've got some decoupling there, some power supply filtering. You can see those bigger, tall electrolytics, some ceramic capacitors there. So yeah, that's all, pretty stock standard. Now, the meat and potatoes of this device will be in here. So those will be transistors. I bet my bottom dollar, because you don't want to be driving a relay directly. There's a bit of a gotcha. The coil that powers the relay will often draw far more current than a microcontroller pin can handle, which is what's ultimately going to be driving this. So you've got these transistors here, which will, or they could be MOSFETs or BJTs, one or the other. Then we're going to have these diodes here, and they are flyback diodes. There's one there. And if you look carefully, there's one squeezed in between there. So because these are through-hole relays, that wouldn't have presented an issue in the reflow soldering. But what they are is they are essentially connected in reverse polarity across the coil, because the coil of a relay is it's like a wound coil, which is an inductor. And the way inductors work is they will have they've got this relationship between the voltage and the current, which involves some basic calculus, but a little bit beyond the scope of this. But the takeaway is that when you have a switched like current going through, or you're switching the voltage going across an inductor, like what you're doing when you're driving it like this, and this is a very sort of basic explanation, you're going to generate, the inductor will generate this this voltage because of the change in current. It tries to oppose that, and that is not good, because it will be many, many times greater than the input that you're driving it with. In this case, a little transistor or is driving it with, and so you'll likely blow that transistor if you just try and drive it directly without this flyback diode. It's a few names for this type of configuration, but it doesn't really matter. It's basically this diode's going across the coil, and then you're driving one side of the coil high and one side of the coil low to open or close, turn on or off the relay. So we've got that diode there. Then we've got some current limiting resistors there. That looks like one of those will be feeding the base or the gate, depending on whether it's a FET or a BJT, going to ground there. So those are, oh, interesting. So that, oh no, there we go. So assuming that's a via down to ground there. So that resistor will probably be tying, what's that? That's a 100 ohm, 100 kilo ohm. Oh no, times 2. So that's going to be a 10K. So these are 10K resistors from the markings there. 100 order of magnitude 2. So 10K. So one of those will probably be pulling up the gate, I would imagine. That's connected directly to ground. So these are going to be on the low side of the relay. I could be, by the way, this could be completely wrong. This is just a quick look and, an engineer's rule of thumb analysis of this sort of thing. So don't take this as gospel. This is just some initial probing, poking around, using a bit of intuition to try and work out what's going on. So it's connected to ground there. So these are likely going to be NPN or N-channel transistors driving the low side. And then so we're going to have, I'd say, pull down at the gate. Then a current limiting resistor on the gate as well, more than likely, going through here to here, to this IC. Now, without even looking at that, although the HCS kind of gives it away a bit as the logic family, but I'd bet that this is some sort of digital buffer circuit or, digital switch. So HCS 14 of 24. Texas Instruments. Yeah, so this is going to be part of this 74 HCS logic line. Now, it's probably not the exact. Oh no, that is a TI part. So this might be more or less the exact one. I'll make sure I get the screen share for this next time so you can see sort of the data sheets I'm looking at. But yeah, so this is an automotive. That's just automotive grade. This could be the wrong data sheet, whether it is or not, doesn't matter. But it's a hex inverter with Schmitt trigger inputs. So it's going to invert our signal, and the Schmitt trigger is going to clean up any noise or jitters and give us a nice, clean, square output. So yeah, pretty much exactly what I suspected. It takes the inputs from the omniport relay, cleans them up, gets rid of any noise, and then uses those to drive the transistors. Now, if these are N-channel, MOSFETs or NPN transistors, that means that gate needs to be driven high, or unless that's a pull up. Who knows? Either way, let's try and control it. We'll see how we go. Just a second. In a very, very high-tech demonstration here, we're going to just take a look at controlling this. So my guess is, there's two ways to go about it here. I'm not going to bother really, you've got a decoupling capacitor there for the rails, a couple of other resistors, whether they're just current limiting resistors to the inputs or not, I don't know. That is the omniport in, isn't it? Yeah. So plug a TRS cable into there. I might move the microscope, I think. Let's hide that. All right. Let's bring this top-down camera back over here. This is going to be very, very low-tech solution here. Oh. We are just going to get some alligator clips, and I suspect that this will either be driven, you drive the pin low and it's got a pull-up resistor on it, or you need to explicitly sort of give it a voltage on the pin there. So I'm just connecting to the tip here with an alligator pin, and this is very, very jank setup. More properly, I'd get an external kind of test platform with the voltage, connect to the grounds, and really probe those points. But I know that that big tab there, that's a pretty safe place to go poking some wires. That is going to be 5 volts, and if this runs on 5 volts, the relay switch on 5 volts, the logic here is going to be 5-volt compatible because there's no other regulators of any kind. So we can safely apply 5 volts to the inputs of parts of this circuit. So let me see if we hear. Hey, do you hear that? That's the click of our relay. Much success. Interesting. So that means that you, in fact, have to drive this with a powered input. So you have to drive it with 5 volts. I mean, this is a Schmidt trigger, so really, like, what's the high threshold here? I can't remember what the voltage threshold will be. Electrical characteristics, positive switching threshold. Okay, so when operating at 4.5 volts, the maximum. So in other words, the maximum guaranteed voltage you need to turn it on. And this is not the typical because the minimum is 1.7 volts. The maximum is 3.15 volts. So really it's around the 2.5 volts-ish. So you only need 2.5 volts to turn the inputs of this inverting trigger here on. So, 3.3 volts or 5 volts, it's going to do the job either way. Interesting that because it's inverting, you're not just connecting it to ground and sort of having a pull up there. But, either other doesn't matter too much. But yeah, you can hear. And if I can kind of wrangle this, so you can see if I can do this upside down so you can see the LEDs. You can see that LED turns on. Hey. And if we connect the ring, although this is going to be a bit harder with the crocodile clip, we'll see the other relay turn on. So you should see the other LED turn on. There we go. Beautiful. So a nice little, let's disconnect this and disconnect power. This is a really nice little box. There's not much to it, and there doesn't need to be. Relays aren't complex devices to drive. You've got your relay drivers in those transistors and your protection diodes. You've got your power regulation and filtering. You've got your input with the Schmidt trigger. It's a really elegant low parts count solution to driving a relay with something like this. So yeah, you don't actually need a microcontroller or anything, which is a very good thing in this economy. That was a terrible accent, by the way. You don't need anything too fancy going on here. So yeah, I guess that's really all we need to look at. That's kind of how it works, what's going on. And it's just it's a really well thought out little bit of kit. So if you need something in the meantime to drive a relay device, then yeah, well done, team at Morningstar. I really like what you've done here. So where are my screws? This is always the #1 challenge. Hang on. Okay. Hang on. Where are our washers first? Washers. So for you, if you're at home and you wanted to control this maybe with like just a momentary foot switch or a toggle foot switch or something like that, then yeah, if you had a little box with some power, and you would need it to be powered, is one of the downsides of requiring that high voltage input rather than just like a closed contact switch input. If you were at home, you could pretty easily DIY something up to control this in itself. It's just, as you said, it just needs a high voltage input. It doesn't have to be 5 volts, anything really. 3.3 volt or 5 volt logic will do the job just fine. You can see the beauty of these slotted holes here. You can kind of just put a screw in somewhere, align it, and then fasten them down. So yeah, this is nice engineering. This is a good start to the day. Okie dokie. Tighten those up. Now, if you guys enjoyed this, hopefully this was helpful to you. The whole intention of these videos is just to shine a light on, interesting engineering, to take a look at, I guess, the parts of guitar pedals and devices and things like that get looked at. There's huge amounts of resources on DIY guitar pedals and analog electronics and things like that, which is fantastic. And really, really informative and useful stuff, and really knowledgeable guys out there. But when it comes to, outside the realm of like niche forums and interest groups and things like that. For your average, guitar pedal DIY, there's not as much information out there on digital systems and, things like that. And it's the kind of thing that I would have really enjoyed when I was, learning this kind of thing. So I hope that was helpful or just informative, or at the very least interesting for you guys. I think it's kind of cool to just be able to take stuff apart. It's purely a curiosity, thing where I just like to find out how stuff works. I just like to take a look and open it up and find out what's going on. And it was a double bonus that we had a customer reach out and ask if it was going to be able to work with his bridge controller, because we want to make sure as much stuff works together as possible. Because as soon as you say to someone, oh no, sorry, technically we could, you wouldn't say this, but technically we could, but we're not going to make this work with our device because it's a different brand. Then as soon as you do that, you're just, at best, you're just alienating the person without needing to. And at worst, you're creating extra landfill stuff that, if they say, well, it can't work with this and it has to, or go buy something else. And if they don't need to, it's just extra waste, extra stuff, which is definitely not what our world needs. So if you want to control this device, hopefully now you know how to do it, and two, how to find a device that is capable of doing it. So that's our Teardown Tuesday on the Morningstar Omniport Relay Switching Interface. Hope you guys enjoyed it. We're still live. So part of being live is you need to go on live. Simon, Q-Tech is not live.